We present adaptive IMLE, an implicit generative modeling approach that covers all the modes and generates high-quality images. In this work, we focus on pre-training-free few-shot image generation setting. The datasets used in our experiments consist of as few as 100 data examples. The scarcity of available data makes the learning process in this setting extra challenging. Moreover, the difficulties associated with generative modeling, such as mode collapse, overfitting, and underfitting, becomes more pronounced in this setting due to limited data. Before we explore our approach to addressing these issues, let us briefly discuss the background and the existing challenges. In the field of generative modeling, one of the main goals is to model the underlying data distribution, and then draw new samples from it. One of the prominent implicit generative modeling approaches is GAN. It involves a minimax game where the generator tries to generate realistic outputs, while the discriminator aims to distinguish between fake generated samples and real ones. Intuitively, the objective of GAN focuses solely on producing realistic outputs and does not ensure coverage of all the modes. This well-documented issue is known as mode collapse. As can be seen in this simple example, GAN fails to capture top modes of the data distribution. A recently proposed method called implicit maximum likelihood estimation aims to tackle the mode collapse issue. IMLE procedure involves generating a pool of random samples, finding the nearest neighbor for each data point among generated samples, and then it adjusts the nearest neighbors to become more similar to their corresponding data point for a fixed number of iterations. This two-stage process is repeated until convergence. This procedure ensures that each data point has a similar generated sample, thereby covering all the modes. Despite mode coverage guarantees, IMLE produces lower quality images compared to those of GAN. We attribute this issue to overfitting and underfitting. This is caused because IMLE treats all data points equally by adjusting the nearest neighbors for a fixed number of iterations, without considering their varying difficulties. In the following example, we can see how IMLE works. Here we can see the data points, some randomly generated samples, and nearest neighbor for each data point. IMLE adjusts the nearest neighbors by pulling them closer to their corresponding data points for a fixed number of iterations. To repeat this process, IMLE finds the nearest neighbors among newly generated samples for all data points. This two-stage process repeats. Here we can see that some data points suffer from overfitting and some from underfitting. To address the issue of mode collapse, overfitting, and underfitting, we propose a generalized formulation of IMLE. Our formulation introduces the concept of neighborhood for each data point. Intuitively, this approach enables adaptation to varying difficulty levels of data points, helping us avoid overfitting and underfitting. In the following animation, we illustrate how adaptive IMLE works. During a training, nearest neighbors will be pulled closer toward their corresponding data points until reaching within the neighborhood specified by green dotted line. Once some nearest neighbor gets within the specified neighborhood, we shrink the neighborhood and find the nearest neighbor for that data point among newly generated samples. The updated neighborhood and nearest neighbor can be viewed here. We should note that the original IMLE would have either continued training with the same nearest neighbors, resulting in overfitting, or would have changed all nearest neighbors, resulting in underfitting. We repeat this process. As we keep training, the neighborhoods around data points get smaller and smaller. In the paper, we provide proof that this procedure is equivalent to maximizing likelihood. So, adaptive IMLE enables us to perform maximum likelihood optimization without needing to evaluate the likelihood function. Comparison to vanilla IMLE shows that our method generates higher quality images and converges faster. Here, we present qualitative results for our proposed method and baselines. Our baselines include recent GAN and diffusion-based models. Our results showcases high-quality outputs while covering all the modes. Furthermore, we can observe that our method demonstrates the capability of producing smooth and meaningful interpolations. Lastly, adaptive IMLE achieves better recall and FID score in all cases, showing both mode coverage and high-quality outputs. For more details, visit our project page. Thank you.